Computational materials discovery operates at staggering velocity. Modern pipelines ingest massive datasets, relaxing structures and predicting thousands of theoretical configurations per second. But beneath this sheer output lies a structural vulnerability in how these pipelines evaluate success. The algorithms overwhelmingly rely on compensatory, additive scoring. In a standard additive equation, a model weights variables like stability, conductivity, and cost, summing them to a high total score. But the math compensates. If a material is cheap but impossible to synthesize, high scores mask the failure, greenlighting a false positive. The Triadic Chemistry specification, or TRC, provides a mathematical correction to this architectural blind spot. TRC replaces weighted sums with a non-compensatory geometric framework, mapping properties across 4 distinct physical and societal layers. It pairs this geometric core with 2 protective mechanisms, a Gaussian stability matrix to quantify deep uncertainty, and a sign-symmetric firewall to lock out dual-use hazards. To build a reliable AI orchestrator for chemistry, the underlying mathematics cannot average out physical weakness. It must actively punish it. The TRC registration maps every chemical system to 3 invariant pillars: form, position, and action. This triadic model starts with form. In chemistry, form represents identity and structure. Its proxy is elemental formation energy, measuring thermodynamic depth. The second pillar is position. This represents phase and context, measured strictly by the distance to the convex hull, or E-hull. This boundary is strict. E-hull is a locus quantity. It evaluates competing phases in a specific context, which is distinct from elemental identity. The third pillar is action, defined by the material's reactivity, kinetics, and functional turnover at its operating activities. The TRC specification integrates these 3 pillars into a single stability score. U equals the cube root of form times position times action. This shift from additive to geometric math changes how a system handles failure. If the action pillar drops to 0, the total U score instantly collapses to 0. A perfect crystalline structure without a viable synthesis route or stable kinetic profile is mathematically useless. This equation ensures the algorithm respects that physical reality. Theoretical stability is only the beginning. A chemical node must survive evaluation across its entire real-world lifecycle. To track this, the triad extrudes downward to form a 4x3 operational matrix, covering 4 layers of the material lifecycle. Layer 1 covers inverse design. Layer 2 scores synthesized material stability. Layer 3 evaluates evaluation fitness, while Layer 4 judges its overarching societal role. Layer 3 is where materials are selected for specific applications based on their triadic fit. This Ashby scatter plot demonstrates the baseline for selection, a constraint-screened Ashby index. Specific quadrants are blacked out by a hard constraint mask. This mask applies a physical veto. Only after a material survives this binary physical screen does the algorithm measure the graded triadic fit of remaining candidates. This 4-layer pipeline ensures optimization is holistic, rejecting materials that are structurally viable but strictly unsuited for their intended deployment. Density functional theory predictions often create an illusion of precision over highly uncertain data. The Gaussian stability matrix, or GSM, provides the probabilistic layer required to navigate this uncertainty. The GSM replaces every static number in the 12 cells of the matrix with a belief distribution. These are modeled as logit normal distributions. Their horizontal axes are strictly locked between 0.0 and 1.0 via logistic mapping to prevent impossible physical states. This approach allows the system to distinguish a high-confidence failure from mere ignorance. This cell shows a narrow spike near 0.1, indicating a known low state supported by solid evidence. Now look at this cell. The curve is wide, flat, and centered at 0.5. This represents deep uncertainty tied to low data coverage or neutral consensus. While both might yield a poor point score, their underlying failure probabilities dictate vastly different responses from the orchestrator. To manage cross-pillar dependencies, the GSM uses a covariance matrix. These off-diagonal vectors map the correlations between the form, position, and action cells. These vectors do not assume the pillars act independently. They parameterize the exact failure of separability between them. This addresses the DFT from one structure confound. Because form, position, and action are often calculated from the same relaxed electronic cell, they can be heavily collinear. The GSM does not hide this confound. It uses the measured conditional dependence to honestly widen the credible interval of the total score. The GSM forces the orchestrator to account for its own ignorance, ensuring that highly correlated predictions cannot masquerade as high-confidence discoveries. The final operational stage of the matrix is layer 4, the Societal Telos. At this layer, the engine follows a strict rule barring cross-substance aggregation. The score is evaluated per substance and never summed to rank overall worth. This boundary exists because of a hazard inherent in chemical optimization: sign-symmetric leverage. Consider this mathematical vector. It identifies the cheapest pathway to stabilize a beneficial compound, but the math is agnostic to the objective. If you flip the sign on that equation, you have just calculated the cheapest pathway to weaponize or destabilize that exact same compound. Because algorithms are sign agnostic, chemical safety cannot be optimized mathematically. It must be enforced architecturally. This is the function of the layer 4 firewall. Net harmful substances, specifically chemical weapons, explosives, and persistent pollutants, are designated as type forbidden optimization targets. If the AI encounters a forbidden target or an incidental hazard, the protocol is immediate. The engine must halt, log the threat, and redact output. True AI safety in automated chemistry is not a tunable parameter. It is a rigid governance boundary that supersedes all efficiency metrics. This is the complete TRC architecture: geometric scoring, uncertainty management through the GSM, and societal governance via the L4 firewall. Yet this framework operates under a crucial epistemic condition. As the stamp indicates, the specification is strictly B3 pending. It is not a proven physical law. TRC is a falsifiable specification. Its validity depends entirely on upcoming empirical separability tests. If those tests prove that form, position, and action are hopelessly entangled by the single structure confound, the triad collapses. The entire engine is deleted from the framework, not reinterpreted. Uncompromising scientific rigor requires building architectures designed to kill their own load-bearing assumptions. Only an engine that survives its own destruction is fit to guide discovery.